Welcome to our seminar. Today we are very pleased to have Vishesh Jain from Stanford, who's gonna tell us how to perturb matrices. Vishesh, please.
Thank you so much, Thomas, for the invitation, and thanks to everyone who showed up. I see some familiar boxes here. So today I'll talk about some joint work with my fantastic co-authors Ashwin Sai and Mehtab Sani, who are grad students at MIT. And as Thomas said, this is sort of a matrix perturbation result. I think it's a nice combination of like sort of deterministic classical and sort of some more recent random matrix theory. So I hope this audience will enjoy it. So let me sort of start with some basic definitions. Okay, we know what like a diagonalizable matrix is. Something if A is diagonalizable, if you can write it as VDV inverse, where B is an invertible matrix and D is diagonal, and a fact which is rather easy to see is that a matrix. So right now I'm talking about complex matrices. But later I'll talk about real matrices. But right now let's do everything in the generality of complex matrices. So something that's easy to see is that a matrix is normal in the sense that A conjugate is the same as A conjugate A, if and only if it is unitarily diagonalizable, right? So not only is it diagonalizable, but you can actually find unitary matrix B such that A is VDV inverse. Okay. So now like one thing that you might ask is, okay, yeah, normal matrices are nice. They have many nice properties, and for instance, the property that one of the properties that we will be concerned with in this talk is spectral stability. So normal matrices have sort of stable spectrum, so you might ask, okay, yeah, like I care to know how far a matrix is from being normal, right? And sort of like one way you can do that is by means of the eigenvector condition number. So what is this quantity? So what you do is you say, well, let's say I have a matrix A, and let's say it's diagonalizable, right? So if the matrix is not diagonalizable, then you're taking the infimum over an empty set, so it's infinite. So if you want this thing to be finite, then you say, well, okay, now my matrix is diagonalizable, and now let me sort of look at all possible diagonalizations, and now I choose the best one, and I choose the best one in the sense that I want the matrix of eigenvectors to be sort of as best conditioned as possible, right? So this you will recall is sort of the standard notion of condition number of a matrix from numerical linear algebra. You want to look at the product of the largest and the smallest singular values, or like the inverse of the smallest singular value, and the condition number is sort of something which tells you something about the precision of computations in numerical linear algebra, for instance. So here you want to know, okay, like I want to sort of quantify the extent to which my matrix is not normal, and then you can sort of introduce this eigenvector condition number. And the point is, well, if my matrix is normal, then this thing is 1, and at the other end of the spectrum, if my matrix is not even diagonalizable, then this is like infinite, right? So either if you want, you can sort of view this as some measure of non-normality, or you can sort of view this as some measure of how well is your matrix diagonalizable, with this sort of understanding that if something is unitarily diagonalizable, then I'm like really happy, and I say, oh yeah, this is amazing, right? This is fantastic. Okay, so this is sort of the general idea, and again, as I was saying, that the reason you care about something like this is that normal matrices we now enjoy many nice properties such as spectral stability, and here is some classical result by Bauer and Feig, which basically tells you that this guy, the eigenvector condition number, it sort of controls how much your spectrum can move under perturbation, right? So let's sort of just see what this is saying. This is saying, well, if I have some matrix A, and if A has small eigenvector condition number, then if I add some matrix E, so E can be any matrix, and I see how much the eigenvalues have moved, they can move basically by this amount, the eigenvector condition number times E, and here E is sort of the usual 2 to 2 operator now, right? So this is some classical result, and this is sort of an important reason why people care about this eigenvector condition number. Okay, so the motivating question here, which was asked by Davies some time ago, maybe 15 years ago or so, is okay. So we know that diagonalizable matrices are dense in the set of all matrices, right? So his question was sort of maybe some sort of quantitative version of that, which is, well, is it true that every complex matrix is close to a matrix which is very well diagonalizable in the sense of having a small eigenvector condition number, right? And so I believe his concrete motivation for asking this question was the following. So he was interested in sort of numerical linear algebra, and in particular this computational task, like this actual computational task. Sorry, is there a question? Okay, maybe that was an accidental unmute. Yeah. So so he was interested in this actual computational task of just sort of I give you some analytic function A, analytic function F, and you want to evaluate that on a matrix, right? Okay. So now you say, well, I know that if A is diagonalizable, so I can write A as V dV inverse, and now FA is V times FD times V inverse. So like, okay, what's the problem here, right? Like I know how to evaluate FD, and I can multiply by V and V inverse. So there doesn't seem to be an issue here, right? So I guess like for like a pure mathematician, sure, there is no issue here. But the problem is that if V has like large condition number, then okay, what's happening in real life, right? So on a computer, if you're kind of trying to do something like this, you can't work with like real numbers or numbers up to arbitrary precision, right? So you have to like work with like sort of finite bit precision, right? And what's going to happen is that if your matrix V is ill conditioned, so in the sense that the norm of V times the norm of V inverse is large, then the computation of like V times FD times V inverse, this is not numerically stable, right? So this is sort of this general thing that if you're working with like sort of B bits of precision, then you can sort of handle sort of condition numbers which are like maybe like polynomial in B or like exponential, I guess exponential in B, right? So I think that's sort of the dependency here, that if you have like a certain amount of, if you're doing these linear algebra operations, and you have like you can handle a condition number which is, let's say, exponential in your bit complexity, but beyond that there is some sort of issue, right? So you might have like sort of these round-off errors and other things, and you might get like just sort of pure garbage. So what Davies said is, he said, well, assuming that the answer to this question here in the box is true, what I'm going to do is the following, right? So if it is true that every matrix is close to a matrix with small eigenvector condition number, then what I'm going to do is I'm just going to perturb the matrix, right? So I'm going to move to this nearby matrix A plus E, which has small eigenvector condition number. Then I'm going to do exactly the same thing, but now I'm computing like V prime times F D prime times V prime inverse, where V prime D prime V prime inverse is the diagonalization of A plus E. And now this guy is fine because the eigenvector condition number or the condition number of the matrix V prime is small enough. So this is a numerically stable computation, right? And sort of to lend some evidence in support of the strategy, I think him and like some other people, and I apologize, I'm forgetting their name. They ran some experiments, and they saw, well, even for computing something like the square root of like a positive semi-definite matrix, for at least like certain examples of A, this strategy works better than whatever existing implementation was in MATLAB, at least in 2007. So I don't know if like after like all of this happened, maybe now there's some updated routines on MATLAB. I'm really not an expert on these things, but I think at least like I think you can look at like Davies' paper or some experiments by Mark Empry, I think, and they show that you can actually get better answers even for something like computing the square root of like like a known matrix, right? So this was sort of the motivation. I should say that these kinds of things moving like sort of perturbing a matrix to get to a matrix with sort of well-conditioned eigenvectors. So this was sort of the example that showed up in Davies' original paper. But since then this has been used in a couple of other things as well. At least a couple of things as far as I know, possibly more. One I'll mention is this recent work on approximate diagonalization of matrices. So sorry, again, is there a question? Okay, I think that was also an accidental unmute. Okay, so yeah, so like one work where this kind of idea shows up. In fact, the things we will talk about is this question of like approximate diagonalization of a matrix. So you have like a matrix A, and okay, it's a non-Hermitian matrix, and you want to find the diagonalization of a matrix which is very close to A, right? So this is sort of, this thing which is called, approximate diagonalization with backward error. And, recently there was this work by Banks, Garza Vargas, Kulkarni, and Srivastav, where, they show that, you can do this kind of thing in matrix multiplication time. And, this was sort of a big improvement over the kinds of things that we known earlier. Also, there was this paper very recently, last year, by Rishik Peng and Santosh Vempala on sort of a solving sparse system of linear equations faster than matrix multiplication time. And again, these sort of regularization ideas show up there, right? So this seems to be like, some sort of useful computational primitive. And, the point of this talk is to sort of talk about, okay, when can you do this thing? How can you do this thing? And, how well can you do this kind of thing? So this is sort of the motivation. Okay. So in the same paper, where Davies asked this question and provided some motivation, he was able to sort of provide some sort of quantitative estimate for like some construction of a perturbation which has some well-conditioned eigenvectors, right? So what he showed, okay, so again, I apologize, this was slightly confusing, and when we were working on this, we were so confused about this all the time. But I think one thing that might be helpful here is that there is some sort of normalization built into the whole talk. So what you can do is you can imagine that A has operator norm 1, and then all of the perturbations will have operator norm delta, right? I mean, the point is that the way that this thing works is that the perturbation is proportional to the size of the matrix. So you can sort of think of the matrix as having norm 1, and the perturbation has size delta. But anyway, what Davies showed is that if I give you, let's say, a matrix of norm 1, then you can perturb it by a matrix of norm delta, such that the new guy has eigenvector condition number, which is something, let's say, 1 over delta to the n, something like that, right? So there is, of course, like also this exponential factor of n to the n. But you'll see in a moment that I won't like focus too much on the dimension bounds, and I'll focus sort of more on the relation of between sort of delta, which is the perturbation size, and how the eigenvector condition number depends on delta, right? So here's like some sort of exponential bound, so 1 over delta to the n minus 1, and he did some actual experiments, and he conjectured that okay, maybe what you should be able to do is you should be able to improve this bound from 1 over delta to the n essentially to 1 over delta, right? Up to some like factors depending on n, and we'll see that for us these will be some small polynomial factors, right? So I'll be sort of fast and loose with these things, but the point is sort of going to be this 1 over delta dependence. Okay, so he said, okay, like by perturbing with a matrix of norm delta, you can improve hopefully the eigenvector condition number to 1 over delta, and he was able to prove this for like some special classes of it. So now I forget what, but maybe it was things like Toeplitz matrices or something. Like I don't know. So to see whether like 1 over delta is the best you can do, or maybe you can hope to do even better. So this paper of Banks, Kulkarni, Mukherjee, and Srivastav, what they do is they show that okay, if you sort of work with a Jordan block, right? So if you work with a Jordan block with eigenvalue 0, then they do some explicit computation to show that no matter what perturbation you choose of relative size delta, you cannot get eigenvector condition number better than essentially 1 over delta. So okay, there is like a bit of a gap here, right? So Davies conjectured this bound of 1 over delta, and these guys had this lower bound of 1 over delta to the 1 minus 1 over n, which is kind of this funny looking thing. And yeah, there is like a gap here, right? So there is a question here, and personally, I don't have like some great intuition about like which of these should be true. Like experimentally, you can imagine that it's kind of hard to detect a gap between 1 over delta to the 1 minus 1 over n and like 1 over delta. But yeah, I think this is sort of like like an open question as to like whether the upper bound is correct or the lower bound, right? But this is like sort of like a very explicit example that you can read in their paper, and it's like some half-page computation. Okay, so for us, the thing that we'll be talking about is the upper bound. And in the same paper of Banks, Kulkarni, Mukherjee, and Srivastav that I mentioned, what they were able to do is they were also able to resolve Davies conjecture, right? So they were able to show that yeah, you can find a perturbation of relative size delta such that the eigenvector condition number is 1 over delta up to the small polynomial factor of like n to the 3 halves. Actually, I believe there is a conjecture that there shouldn't be a dependence on n, and I think I spoke to Nikhil Srivastav once, and he said that yeah, there are people who work in operator theory who care about this kind of thing. So they can sort of work in infinite dimensions. But at least sort of the way that these proofs go, it is like somehow that there is a reduction you do, and that reduction is tight. And because of at least when you work with that reduction, the factors of n are unavoidable, right? So I think there is like some interesting random matrix theory question and some linear algebra question as to whether you can remove this dependence or not, right? But I think for practical purposes, this is not so bad. Okay, depending on who you talk to, this is not so bad. The reason is that I think the condition number really sort of comes sort of in as far as the bit complexity is concerned, the condition number appears as a logarithm. So like n to the 3/2 really gets converted to log n. And I mean, personally, I think of log as constant, but there are people who work in high performance computing who might be like, oh yeah, I got a 6. So these are like important questions, depending on who you talk to. And again, you might say, well, this is all very well. You tell me there exists some e of relative size delta, which has the small eigenvector condition number. But what good is it for me if I cannot find such an e, right? So they actually sort of go one step further, and they tell you, well, not only does such an e exist, but if you take e to be sort of the appropriate scaling of an ID complex Gaussian matrix, then this is going to work with probability 99%, right? So here I put like complex in bold because this is kind of important. And if you remember the title of the talk was the real Davies conjecture, and all of the difference is going to be between real and complex Gaussians, right? Okay, so this is sort of what they showed. And so one question that they ask and Davies ask is, okay, let's say my initial matrix is actually real, right? So A is not a complex matrix, A is a real matrix. Can I sort of while living within real matrices, can I still have this perturbation? Can I still have this regularizing perturbation, or do I sort of really need to sort of enlarge myself and work over all complex matrices, right? So I'll this seems a little bit silly, but I'll come to sort of why this question was interesting, especially from sort of a random matrix point of view. And again, Davies ran some experiments, and it seems that this is true. But even if you sort of look at this proof of this exponential bounding delta by Davies, this already requires you to work over all complex matrices, right? So at least as far as I know, there was sort of no regularization known while staying within real matrices, right? So this was like some sort of issue here. And basically, what we did with Ashwin and Mehtab is, okay, we were able to resolve this Davies conjecture up to some logarithmic factors. So the conjecture was that the rate should be 1 over delta, and we got something like, okay, 1 over delta times root log 1 over delta. And as with the Banks-et-al. Result, the idea is that this is sort of a probabilistic result, right? So okay, even the statement makes no reference to probability. The result is constructive in the sense that we show, well, you can start with your favorite sub-Gaussian distribution of bounded density, real sub-Gaussian distribution of bounded density, and you can take an ID matrix whose entries are copies of this guy, and this is going to work with probability 99%, right? And before we were going to upload it to the archive, so I emailed Nikhil Srivastav, and he said, oh yeah, we were also going to upload a paper to the archive. And okay, so it's a similar result, except here we kind of get this like 1 over delta rate, and they get this rate of like delta to the minus 3 over 2, right? So this is kind of like up to like this factor of like remember that even for complex matrices, the best thing you can do is like delta to the minus 1 plus 1 over n. So this is kind of like optimal, at least sort of as n is large, right? So anyway, so these are the results. And yeah, I'll talk a little bit about the proofs. I think it's cute, but in case the statements are unclear, please ask me questions, and I think now is a good time to pause for a second or two. Okay, so no questions. So let me continue. Okay, so what's going to happen? So the plan is the following, right? So what's going to happen? So I'll do the following. So right now, we have some statement about the eigenvector condition number, right? So this is like, okay, so the way it was defined, if you remember, was like not so easy, right? It was like, okay, you sort of look at the condition number of the matrix of eigenvectors over all possible diagonalizations, right? So it was like an infimum of a condition number. So what we're going to do in like the next 2 or 3 slides is, I'll show you some linear algebra reductions where you can go from the eigenvector condition number to something which is like an object which is like quite well studied in sort of non-asymptotic random matrix theory, and then I'll talk about sort of how in the complex case once you get to that reduction you're basically done, and then we'll talk about like okay, then it will be clear what Briggs done in the real case, and then we discuss some elements that sort of help you overcome these barriers and sort of do something in the real case. So that's sort of the plan here. Okay, so the first thing is, okay, we spoke about the eigenvector condition number, and now we'll talk about the eigenvalue condition number. So the idea is, well, the eigenvector condition number is something that's associated to this matrix of eigenvectors, and the eigenvalue condition number, at least if your matrix has distinct eigenvalues, then without loss of generality, you can assume that your matrix has distinct eigenvalues. This is something which sort of controls move perturbations of like individual eigenvalues, right? So if the eigenvalues are distinct, it's sort of well defined, to talk about like how much each individual eigenvalue moves under infinitesimal perturbations, and this is what the eigenvalue condition number tells you. So this is sort of the formal definition here. Okay, so this was the point here that if I have simple eigenvalues, the eigenvalue condition number tells me sort of the first order effect of perturbations. And formally, the way you define it is you can say, well, let me sort of write down a spectral decomposition of my matrix. So I can write my matrix as lambda I, vi, wi, I star, where v1 through vn are like columns of v, and w1 star to wn star are columns of v inverse, and then sort of the eigenvalue condition number is the norm of vi times the norm of wi star, right? So sort of the corresponding row and column eigenvector pairs. Provided you have this normalization that vi star wi is 1, right? So this might seem a little bit opaque, but if you write out something as a as v dv inverse, then this is kind of the thing you get. And what you're trying to do is you're sort of trying to say something about the angle between the eigenvectors, about the row, the corresponding row and column eigenvectors, right? So if like these guys are like very aligned, right? So if you think about like a good case, right? Like a good case is something like the identity matrix, where like the like v and v inverse are identity, and in this case like these guys are perfectly aligned. So then you get like small eigenvector condition numbers, and then the bad cases when like these guys are close to being orthogonal, right? So this is like just some quantity which shows up, and it controls sort of perturbations of individual eigenvalues, and this is sort of a little bit easier to work with, because instead of like working with this global quantity where you're trying to sort of say something about the matrix of eigenvectors as a whole, now you have a quantity which is like a little bit more local, and you're talking about like individual eigenvalues, right? So that's sort of the first reduction, that instead of working with the eigenvector condition number, you work with the eigenvalue condition number. And I mean, the reason that you can do that is relatively simple, because remember, what is the eigenvector condition number, right? So you write down a matrix as v dv inverse, and then you're looking at the norm of v times the norm of v inverse, right? So now you're looking at the operator norm, and you know that the operator norm is bounded by the Frobenius norm, right? And now if you think about sort of what the Frobenius norm is, this exactly gives you sort of squares of the eigenvalue condition numbers, right? Because the eigenvalue condition number, recall like, okay, so forget about like wi star. Vi is just kind of like a column of your matrix, right? So if you take the Frobenius norm, you will end up with like v1 squared plus v2 squared plus v3 squared and so on. So again, if you sort of do a normalization correctly, basically using the fact that the operator norm is less than the Frobenius norm, you can deduce that, well, the eigenvector condition number and the eigenvalue condition number are polynomially related, and like there's like some polynomial factor in n. So basically, for the purpose of Davies conjecture, instead of working with the eigenvector condition number, you can work with sort of the 2 norm of the vector of the eigenvalue condition numbers, right? So this is sort of the first reduction that we're going to make. And okay, this is sort of really due to this paper of Banks, Kulkarni, Mukherjee, and Srivastav, where they decided that, well, instead of this global quantity of the eigenvector condition number, we should work with the sort of the norm of the eigenvalue condition number. Okay, so this is like some linear algebra, but this is still not so easy, because the eigenvalue condition number is still like, saying something about, okay. So the way that the eigenvalue condition number is defined directly is, you still have to sort of work with these diagonalizations, right? So now, okay, the question is, can you sort of, move beyond eigenvectors and like say something purely in terms of eigenvalues or like something of that nature? So here is sort of the next reduction, which is, instead of working with the eigenvalue condition number, what we're going to do is sort of, work with, sort of the pseudo spectra, or rather the volumes of pseudo spectra. So let's sort of, pause here and see what this is saying. So the pseudo spectra is saying the following, right? So it's kind of like a robust notion of the spectrum in the following sense. So if you sort of look at the resultant, right? So if I have a matrix A and I look at the resultant Z minus A inverse, then the eigenvalues are exactly the poles of the resultant, right? So these are sort of the points where Z minus A is not invertible, and what the pseudo spectra are doing, it's sort of a smoothed version of that, where instead of looking at the poles, you're sort of looking at large level sets, right? So you're trying to say, well, I'm not looking at like eigenvalues per se, but I want to know what are the points where the resultant is large, right? So this is sort of what the pseudo spectrum is, and I'll show you a picture in a minute. But here's like an equivalent characterization of the epsilon pseudo spectrum, and this is some linear algebra exercise that you can try to do. I guarantee you it's not so hard. So for us, the reason that this will be useful is that the pseudo spectrum here, it's just sort of talking about the level sets of the resultant, right? But there is like an equivalent characterization which is inherently perturbation theoretic, right? So the second characterization says is, well, the way I can view the epsilon pseudo spectrum is I start with my matrix A. I can look at all possible perturbations of A by matrices of norm less than epsilon, and then I can look at the spectra that I can get, right? So I'm basically looking at sort of the union of the spectra under all possible epsilon perturbations, right? So that's sort of like an inherently perturbation theoretic approach, and this is sort of what's going to be useful to us, that firstly that these two are equivalent, and second that the second definition is sort of manifestly perturbation theoretic. Okay. So okay, just to sort of have some handle on pseudo spectra and sort of to anticipate what's going to happen. So for a normal matrix, the pseudo spectra are not that interesting because normal matrices behave well under perturbations. And if you sort of think about what the epsilon pseudo spectrum of a normal matrix is going to be, it's just sort of like balls of radius epsilon around the eigenvalues, right? So for a normal matrix, the pseudo spectrum is just sort of like literally like an enlargement of the eigenvalues. For non-normal matrices, the pseudo spectrum can actually be much larger, and this is sort of exactly this thing that you mentioned, which is that for matrices in general, right, the effect of perturbation on the eigenvalues is controlled by these eigenvalue condition numbers, right? The first order effect. So if I have a matrix which has like very large eigenvalue condition number, then the pseudo spectra can actually be very, very large, right? And I'll show you a picture on the next page. But okay, for us, the thing that's going to be useful is that this relation is actually sharp in the limiting sense. So let's sort of think about this for a second here. So imagine that like epsilon is like really, really, really small, so small that the scale lambda I epsilon balls around the eigenvalues are all disjoint, right? So then what you would expect is that, well, to first order, the spectrum is contained in these disks of radius k lambda I times epsilon. So the volume of these disks combined is just going to be like pi times k lambda I epsilon squared, k lambda I squared epsilon squared, right? And what this is saying is that this thing is actually true in the limit, right? So in the limit, this relation is reversible, and if you sort of look at some ball, right? So you can sort of ignore this thing right now. You can imagine, for instance, that all of my eigenvalues are contained in some ball. So what this is saying that the limiting value of my pseudo spectrum is the union of these disks of radius k lambda I times epsilon, right? So this is sort of a reversible relationship, and what has happened now is initially our goal was to control the eigenvector condition number. We said, well, the eigenvector condition number is polynomially related to sort of the 2 norm of the eigenvalue condition number, and now we have this characterization where we say, well, I can study the 2 norm of the eigenvalue condition number by studying the limit of the pseudo spectral volume. And this thing, is something that we will be able to do using random matrix theory. So this is sort of, the high level idea of what's going on. And here is sort of my promised image now. So, okay, so what's going on here? So here, okay, apparently you have like some 10 by 10 Toeplitz matrix with zeros on the diagonal. And the idea is that, well, this is not normal. And, the pseudo spectra are kind of big, right? So, I have like only one eigenvalue at 0. But, in contrast to sort of the Gaussian, in contrast to the normal case, where the pseudo spectra would sort of be small disks on 0, here, even though sort of my epsilon is like 10 to the minus 5 or something, these sort of disks, okay, these disk-like figures are really sort of macroscopic, right? So the pseudospectra are big, and this is because the eigenvalue condition numbers are big. So what we're going to show is that, okay, even if you have something which has sort of arbitrarily bad eigenvalue condition number, if you add like a small Gaussian matrix, then at least sort of the small pseudospectra become are sort of nicely behaved and are small, right? So here what happened is you added like some Gaussian like 10 to the minus 6 times like some okay, real Gaussian matrix, right? So this is sort of even sort of like hinting to this fact that the real perturbations are going to work. And the idea is that, okay, once you did this thing, okay, firstly, the eigenvalues all get split because now the eigenvalues are no longer all 0. But more importantly for us, the small pseudospectra, I guess like the 10 to the minus 6 pseudospectra are just sort of small balls around these eigenvalues, as opposed to being this macroscopically big quantity, right? So this is what I mean by sort of regularization of pseudospectra, and this is what's sort of going to complete this argument that the pseudospectral volume is regularized in the limit, and therefore the eigenvalue condition number is regularized, and therefore the eigenvector condition number is regularized, right? But if you were kind of lost in the last 3 or 4 slides, then this is sort of the picture to keep in mind, and this is the phenomenon that we're going to prove. Okay. So any questions about that before I show you like the one-line argument here? Okay. So now the final ingredient, and this might be familiar to the audience of the seminar, is this. Okay, so let me sort of rewind and say why this final ingredient is coming in. So remember that the pseudo spectrum has these 2 alternate definitions, right? And this one, we say, well, the norm. Okay, I should have put a norm here actually. So the norm of z minus a inverse is bigger than epsilon inverse, but that's the same as saying the smallest singular value of z minus a is smaller than epsilon, right? So this is so it's kind of it's the same thing. And this is like something that's quite well understood, and this is the result that's exploited here. So the idea is, okay, so there is like this classical result of Sankar, Spielmann, and Tang, and what they show is that, well, if you have any matrix A and you add to it like an n by n matrix whose entries are ID complex Gaussians, then you have this scale behavior for the eigenvalue, right? For the smallest singular value. Sorry, my apologies. So the idea is, okay, typically the smallest singular value is at least 1 over square root n, right? So with probability 99%, the order of the smallest singular value is 1 over square root n. But the important part of this result that is going to go into this theorem is not the behavior in n, but how the tail behaves with epsilon, right? So here there is this thing that if you're asking for the probability that the smallest singular value is less than epsilon over square root n, then the bound on the probability decays as epsilon squared, right? And this is going to be important, and you'll see in a second why. But one thing I want to emphasize here is that this result is really a complex result, right? So this is like not true for real matrices, and here the epsilon squared on the right hand side is really sort of coming from the fact that the probability that like a complex Gaussian lies in a ball of radius epsilon is like order epsilon squared, right? So for a real Gaussian, this would be epsilon, and this is going to mess everything up, right? So this is sort of going to be the issue. And with that, sort of let me just sort of give you the proof on one page here, and let's sort of go through this thing. So the idea is that we wanted to compute so there is some normalization. You can ignore this because this is just going to make everything confusing. But the idea is that, okay, we have our matrix A, and we're adding some rescaled Gaussian matrix, and what we want to do is we want to control the pseudospectral volume, right? So what we say is, well, let me look at the expectation of the pseudospectral volume, right? So of the epsilon pseudospectral volume. And this is, basically the same as asking, well, what's the probability that, this perturbed matrix is going to have smallest singular value, which is less than epsilon, right? And this, by the Sankar-Spielmann-Teng result, we know that this is epsilon squared times, some factors. And now, this is kind of basically, the thing that sort of lets you do everything. The reason being that, what we wanted to do is, we sort of wanted to look at, the ratio of the pseudospectral volume. And, because you have this epsilon squared term, you can sort of divide this by epsilon squared and you can take the limit as epsilon goes to 0, right? So the thing I kind of want to emphasize here is not sort of all of these calculations, but really the fact that, when you're talking about the pseudospectral volume, this is, like one way that you can bound this is by integrating over sort of, shifts with respect to z, the probability that the smallest singular value is less than epsilon, right? And your goal is to sort of, want it to be order epsilon squared. The reason being that, if it's order epsilon squared, then you can divide it by epsilon squared, and then you can take the limit as epsilon goes to 0. And, when you sort of, do this thing, then everything works out. And, you get this sort of, resolution of the Davies conjecture in the complex case. So this was, like kind of fast. So let me sort of pause here and ask if there are any questions about this thing, or if, there is some like crucial thing that, I should have clarified and I missed it. So let me sort of pause here. Yeah, so the takeaway here is that, if I give you a singular value bound, a singular value lower tail bound with rate epsilon squared, then, you can just sort of like, along with all of this linear algebra, you can just plug it in and then everything is going to work out. And then, like the quality of the bound you have and, the way it interacts with like n and delta, that's sort of, going to feed into sort of, the other dependencies. But, without like having this relationship between epsilon squared, you're not even in the game, right? So this is sort of the high level message of this calculation. So let me sort of pause here and see if there are any questions.
So did the Shankar, Spielmann, and Teng, did they really consider, on the previous slide, was it a real Geneva perturbation of a complex?
Yeah. So I think there is something ahistorical here. So I think you're right that in their paper, they really considered real Gaussian matrices, right? And I guess like maybe I should have said something like folklore following Shankar, Spielmann, Teng, but I think people still cite their paper for like this result because, I think it's kind of like just a modification of the argument. But yeah, that's a fair point that I don't think like you find this result directly written in their paper. Yep. Yeah, and there is like some question of like the constant here, and in fact, in this paper of like Banks, Kulkarni, Mukherjee, and Srivastav, they even like have this result with the optimal constant, right? So yeah, there is certainly some question there. Okay, so moving on. So now, okay, like you anticipate what's coming here, which is, as I've been sort of trying to emphasize, the crucial sort of random matrix theory fact that was used here was the tail estimate on the smallest singular value of like the smooth analysis thing. And the point is that, well, like in the complex case, we have this decay as epsilon squared, but if I have a real Gaussian matrix, the best tail estimate would have epsilon on the right hand side. And this is because, well, the real Gaussian, right? Like in an interval of like it has like density like constant, right, around 0. So like in an interval of like length epsilon, there's like probability epsilon that you find it, right? So this is sort of the issue. And while you have this issue that like working with like real matrices, you kind of lose like a square amount of your randomness in some sense. The problem is that because the matrices are still non-Hermitian, it's not like they have real eigenvalues, right? So they have complex eigenvalues. So you still have to work in the complex plane. And if you have to work in the complex plane, when you take sort of the pseudospectrum, the pseudospectrum still lives in the complex plane. So when you look at sort of the ratio of the pseudospectral volume, it still needs to be compared to epsilon squared. But now the problem is that the singular value tail estimate only has an epsilon, right? Okay, so the question is, okay, what do you do here? So luckily, somebody this is a problem which also shows up in other contexts, and there was something that had been studied here. So this seems like totally unrelated, but I assure you it's not. So as a tutor, let me sort of talk about like a seemingly unrelated question, which is, okay, if I give you, let's say, like an n by n matrix whose entries are, let's say ID, Rademacher random variables, right? So each entry is +1, -1 with probability 1/2 each. There's like some folklore question, which is it true that, with probability tending to 1, the eigenvalues of this matrix the matrix are distinct, right? So this is, just to say that the spectrum is simple, right? So, in the Hermitian case, this was known due to Tao and Wu. And again, sort of one reason that it's approachable in the Hermitian case is like a big reason that it's approachable in the Hermitian case is that the eigenvalues are real. So, you can kind of, restrict yourself to the real line where, the sort of epsilon kind of tail bounds on the least singular value are enough, right? So Tao and Wu showed simplicity of the spectrum, and then Nui and Tao Wu proved like a quantitative version of this result. And what does a quantitative version of this result mean? It means like, some estimate of like gaps between eigenvalues, right? In the non-Hermitian case, you run into exactly the same issue, that the eigenvalues could be living in the complex plane generally. In fact, I mean, they do generally live in the complex plane. So, in order to sort of, copy this argument of Tao and Wu on some level, you would like to have this epsilon squared behavior, right? So for instance, if somebody asked you a question about, simplicity of spectrum for like, sort of complex Rademakers, then you would be fine, right? So what do I mean by complex Rademakers? So +-1 plus I +-1, where sort of, the 2 +-1s are independent. So then this would be fine. But in the real case, the decay you have is like an order epsilon decay, and you're working in the complex plane, so you again run into the same issue, right? So one sort of important ingredient that shows up in our work is exactly sort of the techniques which were used to resolve this problem, and this was sort of a conjecture for a long time, and in fact the only thing you do is check archives and journals. You might think this is still a conjecture, right? Because this was resolved by Stephen Ge in his PhD thesis, but the thesis is neither available on the archive nor is it published, right? So by some luck you find the thesis, and then you realize, well, this problem has been resolved, and it's a beautiful thesis, beautiful work. I highly recommend it. And not only did he show simplicity of the spectrum, he also proved like a quantitative version of the result, right? And the main insight that he had, which enabled him to sort of sort of get past this epsilon versus epsilon squared issue was the following. So the issue, so what he said was the following, right? He said, well, imagine that Z is 0 here, right? So imagine like if I have like a real matrix and I perturb it by like, let's say even like a real Gaussian matrix. I know that, in the worst case, I cannot get, tail behavior better than rate epsilon, simply because, when A is 0 and E is like an ID Gaussian, I know that, this is sort of tight, right? This is the best I can do. But if I perturb it by a genuinely complex number, in the sense of, having, like a large imaginary part, then you can actually improve the rate from epsilon to epsilon squared, right? And the price you pay is that, well, there is this dependency on the imaginary part of the shift. And, you need the shift to be sort of relatively large for the strategy to work, right? So if, you want some intuition for this thing, if you're familiar with sort of, these arguments which reduce bounds on the smallest singular value to sort of, the distance of like sort of the anti-concentration of like a vector and, like a random vector and like a deterministic vector, which is sort of, like a normal vector to a hyperplane. The point is that, what's going to happen in this case is the normal vector that you're going to end up with is generally two-dimensional, in the sense that, it's not like a rotation of like, a real vector. And I should say that, like, so we say following Ge, but, like there is like also like a paper of Rudolfson and Verschinen on, I forget, okay, so like on delocalization of eigenvectors, and, like these ideas like also show up there, right? There's like, some idea of like real and imaginary correlations. So this is, sort of, now I think, by now, this is the popular idea in non-asymptotic random matrix theory that, when you're sort of working in the real setting, but, you're dealing with like eigenvalues or something, then, you can sort of exploit these complex shifts to go from epsilon rates to like epsilon squared rates, provided you pay this price of the imaginary part, right? So this is sort of the high level idea of like what happens. I mean, the details are okay, something you have to work out, but, once you know that the statement is true, it's not the worst thing to do. And what Go proved, and okay, I guess so he really proved it for like a equals 0, and even like this previous result, and we sort of extended to like like arbitrary, right? So that's like some work, but it's technical improvement. The other thing that he proved is well, a statement on like quantitative eigenvalue gaps. Okay, this is sort of the whole point of his thesis, and the point of his thesis was to show, well, if I have like let's say, okay, so he was looking at the case when a is 0, but even if I have like a real non-Hermitian ID matrix, then I can say something about eigenvalue gaps, and in particular, with like probability 99%. The eigenvalue gaps are like inverse polynomial, right? So these are like not sharp rates, these are just sort of some numbers I wrote here, right? But this is sort of the point of his paper, that once you have these epsilon squared rates, now you can do some union bound arguments, and now you can sort of use this to deduce quantitative bounds on the on the eigenvalue gaps. So these are sort of like two ingredients from random matrix theory that we use. But okay, so now you might say, well, now it seems like maybe I'm done, right? So now you might say, well, I think I'm done, because you just showed me that there is this epsilon squared decay, and it seems to me that the problem was that we had this epsilon rate versus epsilon squared rate. So once I have this epsilon squared rate, then I should just be done, right? Well, unfortunately, no. And the reason is there is this pesky factor of like you need to be sort of far away from the real axis for this epsilon squared rate to kick in, right? So well, what you can say is, well, I have my singular value, and it's like the minimum of these two guys, right? So when the imaginary part is like sort of macroscopically big in epsilon, then sure, I have this epsilon squared rate. But if the imaginary part is like smaller than epsilon, then I have to kind of use this epsilon rate. And now if you think about this for a moment, you'll see like, aha, so now I have these kind of epsilon kind of terms for this each strip. And when I integrate it, I'm going to end up with a factor of log 1 over epsilon, right? When I sort of look at the ratio of the pseudospectral volume. So in the genuinely complex case, I had like an epsilon squared without like any imaginary part. So then there was sort of the epsilon squared and epsilon squared cancel out. But now because you have to sort of use the second bound when the imaginary part is too small, you end up with this factor of log 1 over epsilon. And now there is this sad fact that if you take the limit as epsilon goes to 0, then this thing is still going to blow up, right? So this is not good, because okay, sure, by using this Go kind of bound, I was able to improve the dependence, sort of the ratio, which would have been epsilon. Sorry, 1 over epsilon. It got improved to log 1 over epsilon. But as far as sort of taking the limit is concerned, it's still blowing up as epsilon goes to 0. So now you might say, well, okay, yeah, it seems like still, I made some progress. So let me see if I can avoid taking the limit as epsilon goes to 0, right? Like who told me I have to take the limit as epsilon goes to 0? And I have this relationship where there was a limit as epsilon goes to 0, but perhaps there is a quantitative version of this result which tells me that this kind of thing is true. Let's say up to constant factors or something for epsilon which is small enough, and then I don't have to take the limit as epsilon goes to 0, right? So we thought, okay, yeah, let's do this, and maybe it'll work out. So if you sort of look at the proof of this thing, and you see how small you need to take epsilon, what happens is, okay, as long as epsilon is smaller than this quantity, the proof is going to go through, right? So let's kind of think about what these quantities are. So let me sort of put this on the next slide. So the moral is, okay, I have like some term now which is log 1 over epsilon. I don't want to take the limit as epsilon goes to 0. So now I try to think about, okay, like how small can I take epsilon, and like or rather how large can I take epsilon for this relation to still work. Okay, so the smallest I can take epsilon, the largest I can take epsilon for this relation to work is the ratio of these two quantities. The top quantity is kind of the eigenvalue gap for the perturbation, and this is not so bad, right? Like this is like sort of what Gerst's thesis is telling us. It's telling us that the eigenvalue gaps are going to be inverse polynomial for the perturbations with high probability. The really bad thing is that the other quantity which shows up is the 2 norm of this eigenvalue condition number quantity, and this is exactly the quantity that we're trying to control, right? So what this is telling me is that, well, you can take epsilon as small as, let's say, 1 over the 2 norm of the eigenvalue condition number, but this is the guy which initially could have been very large, and I'm trying to prove a theorem saying that for the perturbation, the eigenvalue condition number is going to be small, right? So now it's kind of like the circular situation that I want this guy to be small, But in order to show that this is small, I kind of need to know that it's small, right? So now you might say, well, maybe I have some a priori estimate on this. But as I mentioned that, even this sort of original paper of Davies, which gave some exponential bound in delta on the eigen vector condition number, this actually used that E is a complex matrix. So nothing was known for like real matrices, let alone for like a random matrix, like a random matrix result, right? So this is sort of the issue that we would like this thing to be large. We would like this thing to be sort of well controlled, but we have like absolutely no estimate on this thing, and this thing could be like really large, which would mean that epsilon is very small, but we're kind of stuck here, right? So does that make sense, or maybe that was too confusing? Okay, so let me sort of say what the final idea is. So the final idea is that okay, we have this quantity which is the 2 norm of the eigen value condition number. We want to control this thing, and we don't really know anything about it, right? So what we do is we use some bootstrapping argument. So what we say is, well, let me look at the event that so what is this an event in? So remember, E is like a random matrix, right? So the 2 norm of the eigen value condition number is a random quantity, and we're saying, okay, let's look at the event that this guy is less than or equal to some number t, right? Again, I have like absolutely no a priori control on t, but I say, well, let me look at the event that this guy is less than or equal to t. Okay, so now what you can do is you can play the same game, because now basically I know that I can work with epsilon, which is about as small as 1 over t, right? On the event that the eigenvalue on the event that this guy is less than or equal to t, I know that I can take epsilon to be as large as 1 over t. So conditioned on this event, I can run the same pseudo-spectral computation, and I see that the expectation of the 2 norm squared of the eigenvalue condition number should be like log t, right? So this is great. I'm conditioning on the event that the quantity kappa 2 is less than or equal to t, and now I get that the expectation of kappa 2 squared conditioned on this thing is roughly log t, right? So you go from t to log t, and now what you can do is you can say you can use Markov's inequality, and you can say, well, conditioned on the event that kappa 2 is less than or equal to t, what's the probability that kappa 2 is bigger than or equal to log t, right? And just by using Markov's inequality or Chebyshev's inequality, you see that, well, this must be like 1 over log t, right? Okay, so this is great. So the way you can put this differently is, if you have like any estimate, right? If you have like any estimate on the probability that kappa 2 is less than or equal to t, you can get an estimate on the probability that kappa 2 is less than or equal to ft, where ft you should think of as log t, and you lose like a factor of like 1 minus 1 over log t in the probability, right? So if this guy is like probability 99%, then this guy is like 99% times 1 minus 1 over log t. And the great thing is that if t is large, then 1 minus log t is small, right? So as long as like ft is large, you're not paying too much for the ratio and the probabilities, right? So it's kind of like self-controlling. Like if ft is large, then I want to run this process more and more. But the good reason is the good news is I can do this because I'm not paying too much in the probabilities. If ft is like a billion, then I'm only paying like 1 minus 1 over a billion in the probability, right? So this is sort of the main thing. So let me sort of put it on the next slide. So let me call this the bootstrap equation. So now we have this relation that if I know something about the probability that kappa 2 is less than or equal to t, I can improve the estimate by losing a little bit in the probability. Okay. So now you might still say, well, okay, this is some sort of iterative argument, but I have like no a priori information on kappa 2, right? So what sort of the initial step where I start, right? So the good news is that for this thing, because like the probability here is controlled by the size of your estimate. The good thing is that you don't really need an effective bound, right? What you can say is, well, since the perturbation is diagonalizable with probability 1, I know that the eigenvalue condition number is finite with probability 1. So there is some t0, right? So this t0 is like totally ineffective. There is some t0 for which I know that the probability that kappa t is less than or equal to t0 is bigger than 0.99, right? This is just like monotone convergence theorem or something. So this gives you your initial estimate, and the great thing is that this gives you a starting point, and even though this is totally ineffective, you can still utilize this. The reason is that the amount you're decreasing in the probability is exactly tied to how good your bound is, right? So you can kind of keep on doing this until FT becomes acceptable, and you don't lose in probability too much. Let's say you start with 0.99, you're like multiplying by some, if t0 is very large, you're multiplying by things which are very close to 1, and the probability doesn't go down too much, right? So this is sort of the main idea, that even with like a totally ineffective estimate, you can start with that and you can bootstrap, and then you can improve this thing, right? So I apologize. I think I'm a couple of minutes over time, but yeah, thanks for your attention. And here's the paper, and I'm happy to take any questions.
Thank you, Vishesh. Thanks a lot for the nice talk. How about some questions?
Perhaps you could just go back to the last slide and go through it a bit more slowly.
Yeah. So I can go through this a little bit more.
How is it that there's is the implied constant in the main theorem ineffective, or
No. So
just trying to see how you can get away with that.
Oh, so think about it this way, right? So think about so T is something, right? Let me actually go here, right? So okay, so what's happening here? So your event is that kappa 2 is less than or equal to T, right? And so firstly, okay, so is this part fine, that you can we had this like log 1 over epsilon quantity, and the point was that you can take epsilon to be as large as 1 over kappa 2, right? So since you had log 1 over epsilon, that's going to be log T, right? So the expectation of kappa 2 squared is basically log T, right? If you ignore the factors of n and delta. Okay. And now this Markov thing is just like a direct Markov thing. Okay. So what's the point here? The point here is that as long as Ft is very large, you're not paying too much in the probability, right? So what you're saying is you're comparing the probability of kappa 2 being less than or equal to T and kappa 2 being less than or equal to Ft, right? If it were the case that for every iteration, I lost something, right? So let's say I had something like every iteration I do, I lose, like 1 over 100 in the probability, or like 1 minus 1 over n in the probability. That would be a bad statement, because that means I can only iterate it like n times or something, right? So imagine if instead of like Ft inverse, you had something like 1 minus 1 over n. That would be a bad statement, because that means I can only iterate it n times. So if I can only iterate it n times, and I'm taking like a log each time, that means my initial estimate better be something like a tower of height n, right? Otherwise I'm screwed and I can't do anything. The thing about this estimate is that the amount you pay in the probability ratio depends exactly on Ft, right? So it's saying, well, if I'm comparing the ratio of T and log T, the price I'm paying is like 1 minus 1 over log T, right? So as long as so if you think about like multiplying these things, right, it's just like going to converge to something, right? If you just multiply this product, and okay, so firstly, what's happening, right? So firstly, the thing is, as long as T is very large, there is like a big gap between log T and T, right? So let's say, for instance, log T is at least like T over 10 or something, right? So you're like actually going down a lot each time, and then you can just sort of multiply these factors out, and if you're doing this for like T large enough, and you have this sort of like geometric series kind of thing, this is just going to converge, right? So that's the point. The point is that the probability bound depends on Ft, and it doesn't depend on n. If it depended on n or delta or something, then you would be in this place where you would need some a priori estimate on your T0, which depended on delta and n. But since it depends only on Ft, you can actually iterate this without needing an effective T, right? So this is like I think one should be able to sort of use this kind of thing in other arguments as well, where you have some iterative argument, but because the gain only, the loss in probability only depends on the size and not on n and delta, you can just sort of repeat it infinitely, like not infinitely many times, but you can repeat it arbitrarily many times as long as you need, without sacrificing too much in the ratio.